Hello, everyone. So, I am, as Louis said, I'm the CEO and Chief Scientist at Evolution AI. So we make a platform for building natural language processing systems, mainly for regulated entities, so banks, government agencies, kind of environment where they're very risk averse. People are a bit worried about using AI and machine learning. They're really worried that the systems are not ethical or they're not going to meet the constraints of the regulator. So it's kind of on us to prove that our systems are robust and they're not doing weird things. So that's what I'm going to talk about today, how to build AI systems which are more robust and less unpredictable. So these are Russian mine dogs. These guys were trained by the Russian army in World War II to run underneath German tanks and destroy them, like this. So the idea was that they'd run under the tank, and then this mechanism would kind of fire, and then these explosives would blow up, blowing up the enemy tank and the dog. The thing is, when they deployed these things in the field, they ran towards the German tanks, and they stopped, and then they ran back again and ran underneath the Russian vehicles and destroyed all of the Russian vehicles, causing complete pandemonium. The problem was that when they trained the dogs, they didn't have any German tanks. They only had Russian tanks, right? And Russian tanks ran on diesel, and German tanks ran on petrol. Turns out the petrol and diesel smell quite different to dogs, and they didn't really get the picture. This is what happens when your training data is not representative of the production setting, which is mainly what I'm going to be talking about today. So this is an example from my own experience. It's a company that we were doing some consulting for. An engineer had built a topic classifier. So their use case was that they had newspaper articles on newspaper websites, and they wanted to know what the topic was. Is it technology, news, entertainment, sport, whatever? So this classifier seems to perform really, really well in evaluation. Had really good test accuracy, really good precision and recall. Except the customers were really unhappy and constantly phoning up and complaining because it didn't seem to be working at all in practice, in production. In particular, things like technology, it was just basically completely perfect, giving completely perfect results, which was weird. So I looked at the data, and it was obvious that what was going on was because the inputs to this classifier were the body text of the web page, plus the URL and like the title of the page and stuff. There was some really bad overfitting going on, and that's because newspapers use really distinctive strings in their URLs for different topics. So in this case, Daily Mail, anything to do with technology is going to have this string science tech in it, which is potentially going to be a problem if you don't do the evaluation properly. In particular, if you allow articles from the Daily Mail to be in both the training data and the test data, you won't realize that this overfitting is happening, and your evaluation metrics will look really, really good, and they won't be reflective of the performance of the system in the production setting. So this is a case of data leakage, which I think has already been mentioned yesterday, and I'm going to give a few examples. And it's a real problem. I see this a lot. So for instance, at the end of this story is that I told the engineer to, instead of doing this kind of mixing up of the data between the training and the test data, to segregate publications so that all of the Daily Mail would either be in the training data or the test data. All of the Independent would either be in the training data or the test data. And this gives a much better indication of how the system's going to perform in practice. And in fact, the accuracy was actually terrible, and was a much better indication of the truth. This next example is really, really similar. So a company that we worked with, they needed to build a classifier for products using product descriptions. So just read the description of the products and figure out what kind of product is this. Is it an electric toothbrush, whatever. The problem, again, is that lots of suppliers can sell exactly the same product. Again, if you don't realize this is going on, and this company didn't realize this was going on, you end up with the same products being in the training data and the test data. So effectively, you've just got duplicate rows without realizing it. Again, your evaluation metrics cannot be trusted in this scenario. And when we fixed this for this company, they their evaluation metrics started to make a lot more sense. ProSurg. So this comes from a Kaggle competition for detecting or predicting prostate cancer using biochemical markers, blood test results, things like that. So there's hundreds of variables. And one of the variables was called ProSurg. It seemed to have really good predictive power. So everyone was using it. It was very powerful. I mean, it's exciting, right? Because it could mean a breakthrough in the etiology of prostate cancer. It could be a new biochemical marker. Unfortunately, under investigation, somebody realized that ProSurg stood for prostate surgery, which meant that these people had obviously already been diagnosed and they'd already had surgery. This was completely useless for any system in production. And this happens a lot actually in competitions, especially because in something like a Kaggle competition, the competitors don't necessarily know what the variables mean. It's just kind of like a whole bunch of variables with different coded names. So there are many cases of this happening, and competitions have been stopped because of this data leakage problem. So this next example, this is really nasty. This is not data leakage, but it's horrible. So this is marketing information from a company called Predpol. They do predictive policing. So in the States, and increasingly in the UK, they use this kind of software to decide where police resources should be going. Where they're trying to predict where crimes are happening so that they can predict where police should be patrolling. Now, some statisticians took a look at Predpol, and they realized that one of the key inputs was historical data on arrests. So, for instance, this is a heat map of arrests for drug use in Oakland and California. And you can see that most of it is kind of in this red bit, which is an area which is predominantly African American, which is a bias, actually, because drug use in Oakland is very evenly distributed between black areas and white areas. So what these guys figured out was, because this was an input to the model, this would lead to more police being deployed to those African American areas, which would lead to more stop and search, which would lead to more arrests for drug use in those areas, and a feedback loop will be set up. And doing some simulations, they were able to show that eventually the use of this system would lead to nearly all of the police resources being devoted to the African American areas, which would lead to, obviously, to a massive racial bias in arrests for drug use. So this kind of thing, there are a few anecdotal stories of things like this happening in the literature. Obviously, it's probably happening a lot more in industry, but because of the lack of transparency in industry, it's not so visible. But in academia, this kind of thing has been happening a lot, and people have started to ask the question, is modern machine learning really intelligent, or is it just performing a trick? So this is really interesting work from Bob Storm at Queen Mary's College. He looked at a competition-winning classifier for genre classification. So this is musical genre classification. So don't look at the dotted lines, only look at the solid lines. What he did was he changed the tempo of musical files very, very slightly. So the tempo change here on the x-axis only goes up to 9%. So humans can't really detect a tempo change of less than about 4%. So for a human, a tango is going to sound the same whether you change the tempo by whatever percentage. It doesn't make any difference. What he realized with this classifier, so it won this competition, it performed really well in evaluation. So the inputs were for pieces of music, audio, and the outputs were the class of the genre. But what he realized was it was really, really sensitive to tempo. And if you could change the tempo just by a couple of percent, and the F-score, so the accuracy would just plummet completely. So the F-score here on the y-axis. And when he looked into this a bit more carefully, he saw that this is the reason. So this is the training data for that competition. So on the x-axis is just the file index, and on the y-axis you've got tempo. So essentially what was going on was that in the training data, each category or each genre or each example, so each of these dots is an example, a musical file. Each of these examples in a particular genre was clustered, the tempo was clustered around a really, really narrow band. So like all of the sambas are at 100 BPM, basically. So what was going on was that this system, this genre classifier wasn't a genre classifier at all, it's a tempo classifier. And it was, he's done a lot of work on musical genre classification. In fact, he did a really nice review of all of the papers about musical genre classification in 10 years. And he made this really astonishing statement in this review, which is, we show that none of the evaluations in these many works is valid to produce conclusions with respect to recognizing genre. So essentially, all of the classifiers in all of these papers could have been doing something completely different to recognizing genre. For instance, recognizing tempo, or the other big scandal in the field of musical genre classification is that one of the big data sets, one of the key data sets in the field, was subject to data leakage in exactly the way that I've described. And in that case, it was that artists were not segregated between the training and the test data. So the same artist would be in the training and the test data. Nobody realized this was going on for years. And this is leading to exactly the same kind of results that I described for product classification and topic classification. So it's a real problem, and it's very difficult to detect. So, some people say, people have really started to seriously say, does this mean that machine intelligence is fundamentally different from mammalian intelligence? This is a mammalian intelligence. She's my cat called Lula. I used to think she's really close. This is in her litter tray. Like when she goes to the toilet, she scrapes up the litter, covers up over herself, and I used to think that's really clever. It's really hygienic. And when cats evolved in the African savannah, this would be really sensible because they're covering up the scent so that hyenas couldn't predate them. So it's just, this is really good case of animal intelligence. The thing is, I put her in. I moved the litter tray into the fireplace. So this is the fireplace. It's not some kind of weird cat prison like someone said to me once. But what I noticed was once she's in there, now she scrapes the brick wall. She doesn't scrape the litter at all. She scrapes the brick wall in exactly the same way. So she's not intelligent at all. She's just doing some weird mechanical thing. So maybe mammalian intelligence is kind of lacking. And people have looked at this. So this is some people have looked at whether cats can tell the difference between shapes, and they can. They can tell the difference really with a high degree of accuracy between triangles and the letter I, for instance. They did a lot of evaluation on this. It's very well established. But then they did a bit more sophisticated analysis, and they found out that actually, for a cat, this triangle shape is exactly the same as the circle shape, and the I is the same as the U, and they couldn't distinguish between these characters at all. And so what was going on here was that really they were looking at the density of ink. They weren't really looking at the shape at all. So I'm not really sure what this is about animal intelligence, but I think it does say that these problems in evaluation, that evaluating intelligence is really, really difficult for mammals and for machines. Maybe even humans are subject to the same thing. So when most people see an image like this, these diagonal lines, they say if you ask them to estimate what the angle of these diagonal lines are, they say about 10 degrees. I don't know what you guys think, but if they're actually completely horizontal, I'm sure you will have guessed that, and you can prove it just by blurring them. So why am I talking about this? I think I'm trying to say these problems are not fundamental to machine intelligence. I think intelligence is always context dependent. It's not like machine intelligence is totally context dependent and mammalian intelligence is totally fluid and is different in kind. I think there's a continuum. And I think that evaluation is very difficult for all sorts of intelligent behavior. So what can we do about this kind of problem? How can we build systems which are robust and are not making the wrong decisions and not doing any weird, unpredictable things? So one very important thing is to understand why your model is making its decisions. And it's really easy to forget this, I think, in practice. So for instance, just to give an example, in the ProSerg case, if someone had done a linear model right at the beginning, really simple linear model, they could look at the coefficients, they could realize that ProSerg was like ridiculously weighted, completely predictive, and then start to investigate and realize that something was going on. But, who wants to use a linear model? Everyone wants to use deep learning, right? So fortunately, you can do very, very similar things, or it's slightly trickier. But this is the case from Facebook AI research, where they looked using, I don't know whether this has been covered already, but something called attention mechanisms, which are essentially asking which pixels in an image are most weighted or being most relied on to make a decision. So this is a visual question answering classifier. You're supposed to ask questions about these images, and it's supposed to give you an answer. So the first column is just what is the question, and this is the test image. The second column is where do humans look in order to answer that question using eye tracking experiments. And then the third column is a classifier that works really well in evaluation for this particular data set. And we're asking which pixels does that classifier rely on to make the decision. So the first row the question is, what is covering the windows? And the human looks at the top of the windows, they're looking for curtains, blinds, whatever. The machine learning classifier seems to be just randomly looking around the thing. It doesn't seem to be showing the kind of behavior that you would expect if it was answering the question in the same way as the human. And the same thing with the second row. The question is, what is the man doing? The human looks at the man, looks at the thing that he's thrown in the air, which is a frisbee. The machine learning classifier basically just looks randomly all over the image. And if you had really good results in evaluation, but your system looked like this, then I think that you would start to question whether your classifier was actually doing what you wanted it to do. And maybe it was picking up on some kind of data leakage or some other kind of weird thing in the data set. That was not going to be, that I think would indicate that the system was not going to work very well in practice. So this is a particular class of algorithms that use these attention mechanisms, but not every architecture uses attention mechanisms. But fortunately, some people have published a paper, researchers have published a paper last year. The reference is all at the end, by the way. So this paper has demonstrated how you can use techniques from this field of generation of adversarial examples. Details are in the paper, but effectively what they're saying is you can take just a vanilla convolutional neural network or some vanilla deep learning architecture and add on this kind of explainability using an all-purpose algorithm. I'm not going to go into the details unless there are questions about it, but just to give you the details on this particular figure, what's going on is the black, the class name, the true class name is in black, and then let's just have a look on the third column. So the true class here is a tripod, and this black thing is a tripod. And what the classifier thinks it is in red, so it thinks it's a sewing machine. And by using this explanation, which has been generated by this algorithm, you can see why it thinks it's a sewing machine, because it's concentrating on these pixels that kind of look like a sewing machine, right? But you can see that it's not concentrating on the foreground objects. It's clearly not focusing on the foreground objects, even if you didn't know what that was, even if you didn't know it was about a tripod, you would have a sense that this is kind of making a mistake. Happy to take questions and go into details on this. It's a bit technical. The other thing that you can do is just to look at some examples. So, the classic case of this would be to look at Word2Vec, the way that in the original Word2Vec paper by Mikolov, they generated some word embeddings, and they showed that similar words that you know as a human, as an English language speaker, know that like king is similar to the word prints, you would expect those to be similar in the embedding space, and indeed they were. So just looking at examples is a really powerful way. So that's just looking at similar examples, but you can also generate some examples. So this is a nice example that came from Google, where they basically took a random image, so an image formed of random pixels, and perturbed those random pixels in order to move them more towards the kind of input that would apply for a particular class. So this is an image classification task. And in this case, they said, show me images, generate some images which look like the class for dumbbell. Okay. Now clearly you can see these are not really good pictures of dumbbells because they've all got human arms attached, right? So this makes you think this classifier has not really got to the nub of what a dumbbell is. It's got so many training examples where there's a human arm attached that it's kind of got a bit confused between a human forearm and a dumbbell. So and these generated examples are a really powerful way of checking that the model is doing what you think it's doing. So all of these examples, all of the kind of failure examples that I've showed you, they all performed really well in evaluation. That's the common characteristic between all of them. They all performed well in evaluation. They all had really good test accuracy, and yet they all completely failed in production setting. So this is really the only message that I'm trying to say here, which is that don't take evaluation metrics at face value. Like accuracy metrics are just a summary statistic. Test sets are just a summary of the data. So you're just looking at a summary of another summary. Evaluation metrics, simple evaluation metrics, I think, are not the end of evaluation. They're just the beginning of evaluation. And so thank you for listening. Get in touch. I'm really, really interested in all of these topics. I'm really interested in creating codes of best practice for building robust AI systems. So get in touch on LinkedIn or by email, or I'm going to be here for the rest of the day or for the morning. And if you want to sign up for our beta, so we have a natural language processing system which can be used to build state-of-the-art natural language processing pipelines, and it has some inbuilt mechanisms to avoid some of the errors that I've talked about today. So if you want to sign up for that, then get in touch or just sign up on that URL. And with that, I'll take questions. Thank you.
Thank you, Martin. Any questions? Oh, yeah.
Thank you for your presentation. It was great. One of the slides you talked about identifying window, right? How a human would do it as opposed to the picture of windows. Oh, yeah. And then the machine is trying to identify the window as opposed to the human. And to me, that's, I mean, the human obviously looks at the windows. The machine seems to be kind of try to locate the space between the windows, right? So to me,
do you think so? I mean,
I just can't tell just by looking at just one photo, but I mean.
Just to be clear on this, so the actual this algorithm is trying to answer a question about the picture. So the question is, what is covering the windows? You probably can't read it, but the question is, what is covering the windows? The answer is blinds. So that's what's going on here. But go ahead.
So I guess my question is, like, you know, when you're kind of thinking about the validity of your model, because machine has a different way to sort of get there, right? Whether it's not a direct way of looking at the window, maybe it's just looking for the spaces between the window in order to identify window. Well, that's not really the question here. So is that sort of type of question you would like to go through when you're questioning validity of the model? Because they have different ways, right? And the other example you talked about is that the tempo, the correlation between that and the genre, right? And then perhaps there's something there, and then it's using just sort of a bunch of correlation to identify the tempos, which happens to be really effective in order to sort of classify with regards to genre. So to me, why would that be invalid? Like,
that's a good question. I mean, that is a legitimate approach to this, which is some people say, Well, if it works, it works. If it correctly identifies the genre, then who cares whether on some like adversarial test set where you've perturbed the tempo, then that's irrelevant to this thing. But I mean, for instance, I showed you the training examples for samba were all at 100 BPM. Well, samba as a genre, they're not all at BPM in reality. So it's absolutely fine if you're only going to test on that one test set. And that's why I gave the example of the anti-tank dogs, because that's the whole point. Everything works perfectly if your test set is absolutely representative of your production setting, and your training data is completely representative of your production setting. But in my experience, that's never the case. It's never the case. And the music genre is a very good example of that. I mean, play a record, play vinyl record, and you will definitely see variations in tempo of more than 1%. And also, I mean, just musicians play music at different tempos, clearly. That data set was completely unrepresentative of reality. And in the case of this what's covering the windows, I think the sense here is that, I mean, if the machine's not even looking at the windows to answer the question what's covering the windows, it could be doing all sorts. It could be picking up on any kind of weird variation in the data set that's a bias. For instance, there was a competition for looking at identifying right whales from audio. So just taking an audio sample and asking, does this contain the call of a right whale? That was a competition that had to be stopped because somebody realized that the file sizes of the audio were correlated with the class, with the label. So if your system is not even listens to the audio, it's just looking at the file size, then you're justified in thinking maybe it's picking up on some weird data leakage thing rather than the actual thing that you're trying to look at. I mean, it's just an indication. This is just one piece of evaluation.
Thank you.
Isn't that the actual definition of intelligent, to look at the most relevant information to make the prediction? Because a learning system it learns from experience, and all the experience he has is that you give it. So the fact that he's using the one single, simplest piece of information to make the prediction, it shows that he's extremely intelligent. Yeah, you're agreeing with me, right? That's my argument here. My argument is that intelligence is context dependent. There's no such thing as an intelligence that's completely context free. And the example, the cat example of the triangles and the circles, it's just that it's not doing what you wanted it to do. It's not. I'm not saying it's not intelligent. I'm completely in agreement with you. It is intelligent, but it doesn't mean that it's doing what you're trying to get it to do. Evaluation is really, really hard. That's the message.
Thanks for a really interesting talk. I just wanted to ask if you feel like this might be an opportunity for us to build more soft metrics into the building of AI, where we put some human input back in the form of early surveys or just kind of a human-based check on whether the algorithm is doing what it should be doing. Yeah, I think that's absolutely the right thing to do. People really don't like that. Engineers don't really like that because it's not scalable. But I can't see any other way of doing this at the moment, because what we're trying to get to the nub of is what is our human-based prior? What do we really think about this problem? And I don't know how else we're going to do it other than the kinds of things that you've suggested.
I think we have time for one or two more questions, but while we do, I'd like to invite our next speaker up on stage, and let's get her set up. Who had a question? Sorry, over there.
Yeah, I'm not sure. No, I think the different one.
Yeah, okay. So on a more low-level, practical level, and following your example of musical classification, would you say it's, generally speaking, a good idea to insert both in the training phase or the validation phase some artificially modified points? The same way that you could put in your training set some musics where you change the tempo to make the training, robust to tempo change, And the same way, for example, that when you train a deep autoencoder, you also add some noise and some scaling of images, for example. Would you say you could do that, generally speaking, to improve the generalization of models?
Yeah, so if you look at the paper that they published for, what's the name of the Microsoft thing for looking at 3D, what is it called? The Microsoft camera that came out that could look at 3D, gave you like X, Y, Z coordinates. Yeah, exactly. So when they trained that, they used it's like a random forest that they used, and there's a really nice paper on that. But the training images that they used to discover gestures and kind of posture, they artificially perturbed them by like adding glasses, like spectacles onto the images and hats and like changing the clothes and things like that to do exactly what you suggested, and I think it's a very sensible idea. But it wouldn't fix the problem with data leakage in that musical genre case, because you've got this data leakage of artists. I'm not sure how to fix that.
Okay.